So what did we do last week? So we looked at two kinds of matches, right? So let me see if I can find the right page. Okay, so we did two kinds of upward transformations, right? So one was a low pass L match. So we found out the values, we found out how to calculate that. The next one was the high pass L match, if I'm not mistaken. Let me see if I can find it. Yeah, so this is the high pass L match, right? We looked at both of those. Okay, so now I think we also looked at what to do if you need to match to a complex load, right? We quickly took a look at it. Let's try to see what happens, right? So let's say you have 50 plus some CL, right? So let's say the CL is some, so let's say minus J 25, right? So it's 50 minus J 25 is the impedance you want to match to. Okay, so what does this mean? You can calculate your CL from this, from if it's minus 25. So CL turns out to be 2.65 picofarads, right? 1 over j omega c is the same as minus j25, right? So that's what you do. Okay, so CL happens to be 2.65 picofarad. So now the way to do it, as we saw last week, is to combine these two into a single cap. So you know that 50 ohms is matched to 200 using a CS, let's say in this case it's CS prime. So you know that CS prime from our earlier this thing was 0.765. We know this is valid, right? I think this was 7.6 nanohenry or something, right? So now we also know that CS prime is CL CS over CL plus CS, right? So of course you know CS prime, you know CL, you want to find out CS, which is part of your matching network, right? So this will give you CS equals CL CS prime over CL minus CS prime. Okay, or actually I think in my notes I have used the other notation, so let's actually stick to one. Sorry, I'll do it slightly differently. So let me see, what have I used in my notes? These are the notes which are posted on the web, so I want to make sure you don't have any confusion, right? So I believe I have used CS prime here, and I've called this CS because that makes it the same as before, right? So what that means is, you know, your CS is 0.765. So let's do it slightly differently. That means your, sorry for the confusion, right? Just to make sure that things are, you know, the same. I don't want you to see this, you know, see the notes on class and get confused, right? Okay, so you know CL, you know CS, so you can find out CS prime. So in this case, it happens to be 1.08 picofarads. You can calculate it out. Very simple. So what that means is, if you use the earlier, I think it's 7.66 nanohenries with 1.08 picofarad, you can match to 50 minus J25. Okay. Okay. So that is for matching to complex loads. Now the other kinds of matching we want to do are matching downward impedance. Okay. Transformation. Okay, downward impedance transformation. So how do you think this could be done? So we learned how to take 50 ohms up to 200 ohms, right? How would you go the other way? Right? So obviously, so let's say in this case, right? So let's go back to one of the earlier examples. I think we had, let's take this example. So if this is 50 ohms, this was 0.765 picofarad, and this was 7.66 nanohenries, right? And we know this was 200 ohms, right? So if you want to go back the other way, the most obvious way, see, these are all passive networks, right? So if you're looking from one port, look at the impedance. If you're looking from the other port and terminate it with the, what impedance you're designed for, you will get the original load impedance, right? So what that means is all you have to do is switch ports. So what that means is if you add a 200 ohm here and look at this, this will be 50 ohms, right? So automatically you know how to have downward impedance transformation, right? So what you would do is you would convert this to from parallel to series, analyze it as a series equivalent series resonant circuit, and go down in impedances. Okay, so now let's find out what equations you would use, right? They'll be very similar to the ones we designed. So let's say you had sorry, this should be 200 ohms. Okay, so let's say in general, let's consider RS first, then we'll go back to this to the earlier case later, right? RL, and let's see, I think do I have the design equations here? No, I don't have the design equations, so let's just do the example straight away, because that is, I think going through the design example for this again is not needed. And this is RP. Okay, so you would convert this to same LS, and you have CS, you have RS, and this is 50 ohms, right, at the frequency of interest. So of course this is called a low pass downward transformer. So let's take an example. So let's say we want to do, so obviously we know that if you want to go from 50 to 200 at at 2.4 gigahertz as we did last week, we'll get the original values what we did for the low pass network, which is I think 5.75 nanohenry for the series inductor, and I think it is like 0.575 picofarad for the capacitor. But what we'll do is we'll do it at a different frequency. Okay, and we want to go from 50 to 200 ohms. Okay, so what are the equations you can design for? So again, you can use the same Q expression. You remember this from last week? Root of RP over RS minus 1, right? So that is still valid for this network, because you can still write the same equation. How did this come from? This came from the fact that RP is RS into 1 plus Q squared. So when you convert from series to parallel or parallel to series, right? So that's how so this Q expression is still valid. Okay, so then in this case it happens to be root 3 again, right? 1.73. So then the next step is, so let's go back. You also know Q in terms of CSRS and CPRP, right? So let's take CSRS first, because we'll find CS, we'll find LS, and then we'll go back to CP. What is this for a series RLC network, right? What is the expression for Q in terms of R and R, omega, and C? It is 1 over omega CR, right? For a parallel it's omega CR, but for a series it's 1 over omega CR. Okay, in this case omega naught CSRS. In this case, so that means CS is, so you know omega naught, you know Q, you know RS. So you can easily calculate this. It turns out to be 0.33 picofarad. Okay, is that straightforward? Okay, so then what is the next step? Now you want to find out Cp. So what is the expression for Cp? Cp is Cs into q squared plus q squared over 1 plus q squared. So you know q, you know Cs, so you can find out Cp, right? So approximately 0.25 picofarads. And then next step is L. So omega. So what is the expression? How do you need to, would you use Cp or Cs for L? Cs, right? So, and this thing is not going to leave me. Okay. Right? So in this case, that happens to be approximately 2.46 nanohenries, 2.5 nanohenries. And similarly, you can also do a high pass L match, right? What will the high pass look like? Something like this. You have C, you have L, and you have we'll call this RP, right? So and then this is the high pass L match for the downward transformer. So in this case, this will be 200 ohms, and you can go through the same set of equations. Okay, it's very simple. So there is nothing fancy to it. So but what do you notice about all of this, right? What is common to all of these networks? So one thing which is very common is the obvious fact that Rp over Rs minus 1, square root of that is Q, right? So what does this mean? What this means is, once your input impedance, I guess the load impedance and the input impedance to which you are matching, both of those are known, your Q is automatically fixed. Okay? So what that means is, your bandwidth of your match and so on, all those things are fixed, right? But you don't want that. You want to independently control Q, because you may have requirements on how narrow band you want your match to be, right? So the main problem here is, how many degrees of freedom do you have? You have 2 degrees of freedom, L and C, right? But how many things do you want to set? You want to set Rp over Rs, right? You want to set omega naught, and you want to set Q, right? So that's an obvious problem. Okay? So now we'll move on to the next kind of match, which, yes? Yes, but what you need to do is, the reason, so the way you use omega naught is to make sure, see, all these transformations, series to parallel and parallel to series, right? You design them for a particular frequency, because in general, if you try to convert series to parallel or parallel to series, right, your components will be frequency dependent, right? So what we are trying to do is find fixed components to match at a particular frequency, right? So obviously that means that the value of the components is going to depend on the frequency of operation. So that's why you want to set it. If you want to match, let's say you want to match your input LNA input at 2.4 gigahertz, that means that your L and C have to depend on some way on omega naught. Otherwise, what will happen is, if you try to design for these two, you will get some totally random omega naught, right? You might end up matching at 10 gigahertz. At 2.4 gigahertz, you will get no transfer of power at all, right? Okay, so then we'll move on to the next kind of match, which is the pi match. Okay, you will see why it's called the pi match. So what do you do? So let's take the simple case, right? So you have a C and you have an L. So you want to add one more degree of freedom. Okay, so let's do it in this way. It's called the C1 and C2. Now you can understand why it's called a pi match, right? You're basically adding one more component to make sure that you get a third degree of freedom, and you can set Q also. Okay, and obviously the shape itself suggests that it's a pi match. So you have Rn and you have your Rp. Okay, so this is called the pi match network. Okay, and this happens to be the low pass pi match network, right? Obviously, because at very low frequencies, capacitors are open circuits, inductors are short circuits. That means that you're going to pass the signal. At very high frequencies, capacitors will short the input signal to ground, and you won't pass any signal through the inductor, right? So this is the low pass pi match. Okay, so how do you analyze this circuit? So the easiest way to do this is we'll redraw it slightly differently. So we'll decompose this inductor into two series inductors, and then we'll see if you can recognize. Let's call it L1, L2, C2, and we'll call this. So we'll decompose it and consider two sides of the network. Okay, what do you see on this side? You see one L match, right? On the other side, you see a second L match, right? So what we'll try to do is we'll try to analyze each L match separately and then combine them together. Okay. So what you have is, so before that, before we split up and analyze differently, if you just look at this network, what you'll find is, if you just take this right side L match alone, right, you'll get a certain impedance looking in here. We'll call that the intermediate impedance, Ri. Okay, and once you match it perfectly, the input impedance looking in here will also be Ri, so that you can cascade it directly. Okay, so the impedance looking in for the left side L match is Ri and the right side L match is Ri. And what you'll find is, you can define two Qs. So you can define a QR and a QL, which is Q right and Q left, right? Because each side is an L match, and for those L matches you can define a Q. Is that clear? Okay, so let's start considering it one by one. So let's look at the right hand section. Okay. Yes. Okay. So what we're going to do, right? You split the inductor into two. Okay. So L1 and L2, and you consider the intermediate point. Okay. And what you notice is, once you have split it this way, each section, the left hand section and the right hand section, is an L match. Okay. So once you, okay, so if you just consider the right hand section alone, you have an RP, you have L2, C2. So looking in, you'll have a certain impedance Ri. Let's call it Ri. Okay. And similarly, once you are trying to match to a particular Rn, right? So if you had that Rn here, you would have a certain impedance Ri looking in backwards into the other L match. Assuming that Rn is matched to Rp properly, once your network is designed properly, your Ri looking in left and looking in right will be equal. Okay. So what we are going to do is, we are going to take that as a condition, use that to design L1, L2, C1, C2. Is that clear? Okay. So what does the right hand section look like? So you have L2, C2, you have Rp, right? And input impedance is Ri. Okay. So now you can define a right Q. What is this Q? Right? Actually, it's Rp by Ra, right? Remember that it's always Rp over Rs minus 1. It's not Rs over Rp, it's Rp over Rs minus 1. In this case, you're converting parallel to, remember, in most cases, when you convert parallel to series, the resistance actually goes down, right? In all cases, actually, right? Because Rp is Rs into 1 plus Q squared. So Ra is actually lower than Rp. Okay? So this is the relation for QR. And you also know this is equal to omega naught L2 over Ri, right? For the series, so this one you can rewrite it as, so you have Ri, you have, let's say, C2S, and you have L2, right? So similarly, you know that your omega naught L2 over Ri is also the Q of the right side network. Is that clear? Okay. So now we are also going to look at the left hand section, right? So if you look at the left hand section, so you have L1, C1, and you have Ri here, right? So remember, at resonance you can replace the right hand section just by Ri. Is that clear? So if you look in the left hand section, you have you have C1, L1 and then Ri. Okay, so now you can define a Q left, which is that right? Because in this case your Ra is a series component. When you convert it to a parallel RLC, your Rn will be larger than Ri, right? So in this case your Rn is your Rp, Ri is Rs. So your Q for the left side is root of Rn over Ri minus 1. Is that clear? Okay. Now you can also show, what I'll do is, because it's a little bit of like a 3-page derivation, I'll post the derivation on the class website. But you can also show that your overall Q is Q left plus Q right, the overall Q for the match. Okay, you can show that using like energy conservation and so on, right? You can show that you consider the energy stored in the left side network, right side network. You can show that overall Q is QL plus QR. Okay, so we are going to use this to design Q. So the way to proceed, obvious way to proceed is, you know your design Q. Let's say you want to design for a Q of 5, you know the left hand side. So QL and QR depend on Rp over Ri minus 1 and Rn over Ri minus 1. You know Rp and you know Rn, right? Those are part of your design parameters. So then the next thing is to find out Ri, right? Okay. So one design equation we find is Q equals okay, this is one major design equation. Okay, so now let's try to do an example, right? The rest of the derivations are fairly easy, because once each side is an L match, right? Once you have this equation, you know the Q right, Q left, you can design each L match separately, and that's it, right? Very simple. So let's do a quick example. So let's do the same thing, right? Rp equals 200, Rn equals 50, so 200 ohms and 50 ohms, and 2.4 gigahertz, right? But we are going to add an extra condition that the Q should be 10. What was the earlier Q when we did this using the L match? 1.73, right? Root 3. So it's very small, which means it's a very broadband match. But suppose you need a very narrow band match, right? So that let's put this condition that the Q is 10. So first step is to find out Ri. Okay. So 10 equals 50 over Ri minus 1 plus minus 1, right? Now this is an easy thing, right? You just square both sides and so on, right? It will end up being a quadratic equation. Or the other, some people might find it easier to iterate, right? You put in some values, you'll get a certain left hand side, right hand side, so you know how to modify Ri, right? So for example, you can try, let's try the iterative method. So let's say we try Ri equals 10 ohms. Okay, so what is the left hand side? So left hand side is of course 10, but right hand side is root 4, right, plus root 19, okay, which happens to be 6.36. Okay, now which way would you move Ri? It needs to decrease, right, obviously. Okay, so now let's try. So let's try Ra equals 4 ohms. Okay, so what does this give? 50 over 4 is 12.5 minus 1 is 11.5 plus root of 49, right? So this gives you 10.39. So yeah, you can keep iterating. I mean, obviously I'm giving you values which bring you closer very fast, right? So in the real case, yeah, you may need to do a little bit of calculation, but in the end, so you'll keep doing. Okay, so you keep doing this, right? So you reach the final value of Ri, so which happens to be very close to 4, right? Obviously, and it's slightly higher than 4 because you got 10.39. It happens to be 4.3 ohms. In this case, you can try it out. You can solve the quadratic and back home and confirm that it is 4.3 ohms. Okay, so what is the next step then? So now you can find out here. Once you know it's 4.3, you can calculate Q left, Q right, and then based on that you can calculate L1, L2, C1, C2, and so on. So let's just go through that process. What is QL? Root of Rn over Ri minus 1, right? Which is root of 50 over 4.3 minus 1, which happens to be 3.26. So similarly, right, you can show that this is 6.74, or you can say 10 minus 3.26, right, whatever, okay. Okay, so now you have found out QL and QR. Now it is very simple to go back to your L match equations and calculate L1, L2, right, all those values. Okay, so what is L1 is omega naught, Q left over omega naught times Ri, right? What is this? This happens to be like, let's say you get 0.93 nanohenries. Not let's say, you calculate it out, you get 0.93 nanohenries. Okay, so you know QL, you know Ri, you know omega naught. Very straightforward to calculate L1. Yes.
Why did you put this condition of impedance between both sides of the?
So what you'll find is, it is not a condition. Actually, if your circuit is perfectly matched, right, you'll find that the intermediate impedance, if you put in a 50 ohms, once you are perfectly matched, if you put a 50 ohms on one side and look in here, you'll get 4.3. If you put in 200 ohms. Similarly, if you put in 50 ohms here and look in left, you will find Ri, okay, when it's perfectly matched. Okay, so it is not remember, Ri is not a real impedance. Okay, it is just some kind of the circuit impedance at that portion of the network. Okay, it's not a real impedance. So that is the reason why we applied that condition, because if you had a real network, if it was well matched, then you would have that case. Okay. Similarly, L2 is QR times Ri over omega naught, right? Because each one of those resistances, right, Ri is for the left side network, Ri is in series with L1, right side network, Ri is in series with L2, right? You see that? Actually, let's see if I can find the right page. 46, okay. Yeah, so if you see, you're looking at Ri here, right? So it is in series with L2, so the Q expression is omega naught L2 over Ri. Similarly, for this one, it is in series with L1, so it's omega naught L1 over Ri, right? So this happens to be 1.92 nanohenries for this particular case. So now, obviously L1 plus L2 is L, which is 2.85 nanohenries, right? So now you have found out L, so one parameter. So now we'll go back to the left side and try to calculate C1. So you have L1, you have C1, you have Ri, and looking in, you have 50, right? So you convert this to the parallel, right? So of course you have Rn, which is 50. So let's call this Rn for a general case. This remains C1. This will become what is called L1P. Let's call it L1P. which is the parallel equivalent, right? So what do you know from this? So since they are in parallel, you know Q in terms of C1 and Rn, right? For a parallel RLC. So we'll use that. Right? Yes.
We calculated the inductance.
Yes.
So we had one series network and one parallel network.
Okay. Let's go back to page 46. So if you decompose, okay, if you just look at the right side L match, you will convert it to a series RLC, right? And the left side you can convert it to a parallel RLC. That is right. Is that what you meant?
No, when we calculate this quality factor for QR and QR,
Yes.
we had L2 equal to QR into Ri by omega.
Yes. So both of these are series. Because so if you just consider the left side alone, right? So where does, if you consider the left side alone, you can replace the right side by Ri. Right? You have Ri here. Is that right? So let me add it in red here. Okay? It's not a real impedance. What is the Q of this network? It is actually omega L over R. This is actually a series R. Right? Now you can convert this to a parallel, so in which case you get Rn, but you will get L1P. Right? For that parallel network, it's Rn over omega naught L1P is the Q, and the two Qs are equivalent. Right? But remember, we use that relation to actually calculate conversion from one side to the other, right? So either one of the Q relations will work. In this case, it's a lot easier. It's more straightforward. You know Ri, you know Q, you can find out L1. So omega naught L1 over Ri. Similarly, since this is Ri, you look at this right side network. Again, Ri is in series with L2. So you'd use the same series expression. Is that clear?
So we could have directly with the RP and RN.
You could have. The difference is, if you used Q of, you mean for this case, right? You could do that, but then what you would get is, no, expressions will be different, but what you will get is actually L1P. You won't get L1. Because you have to do the resonance, you convert the series to L1P in parallel with Ri, right? With Rn actually. That's what we are doing right now. If you see, that's what we are doing, right? You convert this. Now obviously for this side, sorry, let's go to black. So for this side, what is Q? Omega naught L1 over Ri, right? And for this side, Q is Rn over omega naught Lp. And these two are the same because the networks are identical. Okay, so if you do it this way, then you'll get Lp. You'll need to back convert back to L1, right? This is just a more straightforward way, because yeah, of course you know the relation between Lp and Ln, Lp and L1 in terms of the Q again, right? Okay, so for this parallel network, you know Q, right? So that's what we are doing. Just omega naught C1 Rn. So now automatically C1 is, right? You know all of these. So in this case, it happens to be 4.32 picofarads. Is that clear? Okay. So again, now we'll go to the right side. So input impedance is Ri, you have L2, you have C2, and you have Rp, right? So I mean, you would normally convert this to Ri, and of course this impedance is Ri. So you have what is called C2S, which is a series equivalent, and you have the same L2. Okay. Okay. So now again you can say Q right is, you can just use this side. It's a lot easier. Omega naught C2 Rp. Right? You can use this side or this side. If you do this side, again you will get C2S and you will have to back calculate C2. If you use this, just this portion alone, It's a lot easier. Okay, so what is C2 is QR over omega naught RP, okay, which is 2.24 picofarads, because you know QR, you know omega naught, you know RP. Okay, so the final matching network, so we already know what it is. So you had 50, right? Sorry, you had 200, and you were trying to match it to 50 ohms, and this is C2 is 2.24, this was 4.32, and this was 2.85, and this is your final matching network. Okay, yes,
You go that right side.
yes,
That is like omega naught C2 RP.
yes,
In general, like for any network, we cannot just like the expression we calculate in that L, C, and R all three are in hand.
yes.
Where L will be parallel given my input source doesn't have any input. No, if there is a L is coming in, L is coming in series. Right?
L2 is always coming in series, right? So I mean we looked at this, right? So we try to bring it to the closest possible form, either a series or a parallel resonant circuit. So in this case, because you already have one series element, it's going to be very difficult to convert that to a shunt element, right? So it's a lot easier to do a series to parallel conversion here and do a series equivalent circuit, right? And obviously the Qs in these two are again equivalent, right?
No, how did I get the Q of the first network?
The Q of this one. So remember, so what is the Q of this network?
That will be 1 by omega naught C2 is R.
Yes, Ri. What you can do is, you know relationship between C2S and C2. If you plug that in here, right, it will cancel and you will end up getting Ri equals Ri, right? Because Q is in terms of Ri or Rp, right? So they are just equivalent. So in these cases, the overall Q of the network, you can take it to be the Q of this portion, for example, right? The main reason is we can do that is because remember when we looked at just the plain old series RLC or parallel RLC, the Q could be expressed in terms of just these two, right, which is omega naught L over R for a series equivalent, or between these two, right, as 1 over Ri omega naught C. You can use either one of those. The main reason is energy is shifting between the inductor and the capacitor, right? So if you want to find out the total energy stored, you can use either the total energy to peak energy stored in the inductor. When at that time, when you look at the peak energy stored, the capacitor will have zero energy stored, right? All the energy has moved to the current in the inductor, right? So that's why those two expressions are equivalent.
In a sense, we can say that our L match or I match requirement is based on the bandwidth that we are looking at.
Okay, so the pi match, that's right. In the case of the L match, you don't have any control over how much bandwidth you can design for.
Basically, it comes out that it has a very low Q,
which means a very wide bandwidth, right? So now what that means is, if you want a much narrower Q, right, you just cannot design it with an L match, right? You have to go in for a pi match. So you might get a case, right? I mean, when you go into design an LNA or something like that, right? You'll be given, it needs to match over. So I'll give you an example. So you're designing for, let's say the wireless LAN, right? You have a certain band, maybe 2.4, 2.41 to 2.485, I think 2.405 to 2.485 gigahertz. Okay, that's your bandwidth. So what that means is your LNA in the receiver should be well matched in this band. Now you can't go ahead and say I'm matched outside, because what that means is you'll be picking up stuff from other bands, right? Nearby bands. The advantage of having a narrower response is you can actually cancel. You get some suppression of signals out of band.
Yeah, in a sense, suppose you are working for that broadband signal.
Okay.
This particular signal is matched to that 200 ohm for that particular frequency. Now, if our match is poorer, then
when you say match is poorer, do you mean a lower quality factor or a higher quality? You mean a lower quality factor, I assume.
Yeah, means it is not matched. Suppose I have a bandwidth from 2.2 gigahertz to 2.4, and my signal is matched at 2.2 gigahertz, where it is entirely matched.
Okay.
And I have a quality factor such that at 2.2 it doesn't match properly.
Okay.
You can have that return loss problem whereby single.
Exactly, that's right. So which is why you want to define your queue also, right? That is the main reason why you want to define your queue, right? Okay. So now what did you notice about Ri? Sorry. So what did you notice about Ri? In this case it happens to be less than both Rn and Rp. Okay. So what you'll see is for a pi match your Ri will always be less than Rn or Rp. Okay. So you might find cases where you are trying to match 10 ohms to 50 ohms. Okay. What that means is your Ra may end up being a couple of ohms, 1 ohm, right? So at that point you'll have to start worrying about, if you're having a wire connecting from the circuit to your matching network, what is the resistance of that wire and so on. So you have to be a little bit careful about Ri. Okay. Okay. So now, L match we looked at. So we have different kinds, right? We have low pass and we have high pass, and for each one of this we had and up. Similarly we had down and up. Okay. So the advantage of of the pi match is that you can do either down or up with the same topology of network, right? So you don't have this separate down and up because you have the freedom of choosing Rn and Rp differently. So what will happen is instead of 250, if you use 50 and 10, your Ri you'll just have to design for a much lower Ri. That's all. Okay. So in the case of pi match, okay, so you only have two kinds. So which is your low pass, which we just looked at, right? Right? What is your high pass going to look like? Right, capacitor in series and two shunt inductors. In general, which would you prefer? Why?
Capacitor gives a direct separation between the two.
You would prefer a low pass because what?
Sides.
That's right. The reason you would prefer it is because you don't want two inductors. Remember, inductors are huge. Okay, in any IC process, for typical values. So we are looking at the values, right? You're getting a few nanohenry and a few picofarad. Okay, a few picofarad will probably consume a few tens of square microns. Okay, whereas if you get an inductor which is like a few nanohenries, it will occupy 500, 600, a square or a circle which has a diameter of, quite often it could start anywhere from 150 microns to, quite often if you want higher Q you might want 500 microns, something like that. Okay, so yeah.
In this case, L1 plus L2 would be less than L also.
Yes, but the difference is, so here you have L, so you have C1, C2, right? L1, L2, C. The difference is here you have a single inductor. So remember that Ri, the intermediate impedance, is actually a fictitious impedance. The real lumped network, you're not going to create L1, L2 separately. You're just going to design a single L. Okay? Whereas here you need two physical inductors. When you do two physical inductors, that's always much bigger than just creating one larger inductor. The reason is you'll need to make sure each one behaves separately, you'll need to have a certain distance between them, because how do you create inductors? You're going to use some transmission lines, okay, on your chip. If they are too close, what happens? You'll have magnetic coupling between them, you'll have interactions between them, right? You don't want that, okay? So usually you will prefer this, but you might find cases where you might want this if your inductance values are small enough, or if you don't worry about area. And quite often you might choose either the L match or the pi match depending on other factors. For example, let's say instead of an LNA you're trying to match a power amplifier to an output 50 ohms. Okay, so you have some power amplifier with a DC and AC and so on, right? So what happens if you use something like this? Output has 50 ohms, your circuit is trying to drive this, right? What happens to the DC, right? For inductor is short for DC, capacitor is open, right? So what that means is the DC output voltage of your amplifier is completely transparent to the external world. You definitely don't want that, right? So you may end up choosing something like this, or maybe one of these L matches which has a series capacitance, right? Otherwise, what you'll have to do is, to make sure your DC doesn't pass, you'll have to add an explicit very large capacitor in series. Okay, capacitor. Yes, that's right. So biasing the output node is a problem, right? That's the reason why you'll need an external, not an external, but a separate capacitor if you choose the low pass. Okay. Okay. Now, what I'll do is, because we need to move on to other things, okay, I have some more notes, but I'll post them on the web. You can take a look at them. You'll be using them very rarely, but you should still know them, okay? So the kind of match, the other kind of match is called a T match, and you'll see why it's called a T match. So it looks like this. You also have three components. So you have L1, L2 and C. Okay, you have RP and you have RN. Right, you have a low pass T match and a high pass T match. Okay, how would you analyze this? Right, that's the most easy obvious way, which is you split the capacitors into two parallel capacitors. Remember, it's almost like a dual of the other network, right? Very similar. So you split this into C1, C2, L1, L2, right? And remember that C is C1 plus C2, right? Just like L was L1 plus L2. Now, the interesting thing about this is you also have an intermediate impedance here, okay, Ri, and it so turns out that in this case you will find that Ri is greater than Rn and Rp, okay, in this case. The reason that happens is because if you notice each one of these L matches, right, this L match is an upwards L match and this is a downwards L match, okay. In the other case you are doing a downwards L match and then an upwards L match, right? Is that clear? Again, that will depend on, if you can afford two inductors, it's the same thing, right? You may end up preferring something like this, which is the high pass, because you only have one inductor. You don't care about the DC at this point. Yes, we are coming to that, exactly. So that is the next thing I wanted to talk about, which is for pi matches and T matches. So let's take this pi match, right? So it so turns out that your inductor is not ideal, okay? It has its own capacitance, resistance and so on. What you'll find is, so you'll have inductor comes with its own parasitics, okay? If you use this kind of pi match, you can actually absorb this into these capacitors, right? So if this, if the total capacitance you need is some, let's say 1.5 picofarads, and the inductor already has a parasitic capacitance of, 100 femtofarads, you would use 1.4 picofarads as the physical capacitance, right? And you get the extra capacitance from this. And of course, the other advantage is the matching network will not be sensitive, because you have a large capacitance in parallel with the parasitics. It won't be very sensitive to the parasitics of the inductor. Okay. Similarly, for this one, right? You have this parasitic coming in parallel with C, so you may end up preferring this one over this one in some cases. So it all depends on what is the value of the inductance, how much parasitic capacitance it has in parallel, right? How much area can you afford? So you'll have to trade off all these things when you are designing your circuit. Okay, is that clear? Okay.
So you can very well predict that parasitic capacitance, how much it will be.
So you'll be using simulators to simulate your inductors. Okay. Usually you'll need to do some kind of electromagnetic simulation to calculate your inductors and its equivalent circuit around your frequency of interest. Okay, that's what you'll do. We are going to be using this software called Acetic. I think I put it up on the CAD page. I don't know if any of you have seen it, but we'll be using this software called Acetic, and it is being installed, so it will be done by probably this weekend or next week. Okay, So what you'll have is, your first project will be to design an inductor using acetic. Okay. So what I'll give you is, I'll tell you the inductor value is going to be, let's say 3 nanohenries. The Q, I want a Q of 10, and right, and something like that, right? Because I want to operate at 5 gigahertz, right? What you'll do is, you'll go in, use the tool. The tool allows you to change the dimensions of the inductor. So next class on Friday, right, we'll go through the design of RF inductors. We'll see what needs to be done, right? How things, what kind of inductors options we have, right? What are the characteristics of the inductors we are going to be worried about, right? So we are going to look at all of that in next class, and then you are going to go, use that in the lab the following week. I think on Monday I'll be announcing the first project, which is to design an inductor. Okay. So then what you'll do is, you'll have a simulation assignment where you'll be asked to design a matching network. So what you're going to do is, you're going to do some hand calculations to, let's say, a pi match, and you're going to design decide your L and C values. You're going to put it in your simulator, put in LC values, you're going to match it, it's going to look fine, I hope, right, if you calculate things correctly. After that, I'll make you design that same inductor in acetic. By the way, it doesn't take very long, okay? If you, optimization takes a little bit of time, but it shouldn't be too bad, okay? Then what you'll do is, you'll put that inductor back into your circuit, matching circuit, and then find out how it affects your match. Does that make sense? Okay, so we'll meet next on Friday at 11 o'clock.